Welcome to our exciting observation panel with panelists who are coming to us from all over. If you guys want to go ahead and introduce yourselves.
Do online people want to go first? Trevor, do you want to go?
Sure, yeah, I can start. Hey, my name is Trevor Dorn Wallenstein. I'm a postdoctoral scholar at the University of Washington. My research focuses on massive stars, especially evolved massive stars that have left the main sequence. I think these are some really fascinating objects that we can learn a lot of really interesting stellar astrophysics from. Also, because I'm pretty certain it's against the laws of Zoom to have a dog and not show it off. Here is Blind, who is very clingy and won't leave my lap. So she's going to be here with us.
Melinda?
Hi, I'm Melinda Soros Furtado. I'm a new Hubble Fellow at the University of Wisconsin-Madison. I work on transient searches in open clusters, and I'm very interested in pulsational variables and rapid rotators therein. Yeah, thanks for having me. I do have a dog, but he's downstairs. So.
And Keith?
Hi, everyone. I'm Keith Hawkins. I'm an assistant professor of astronomy at the University of Texas at Austin. I am sad I'm missing you all in person. I have to teach and do panel stuff. But I work on stellar spectroscopy, so really into stellar chemistry and what we can learn from the chemical composition, the detailed chemical compositions of stars across the Milky Way.
And I'm Dominic, so I'm a research fellow at Leuven in Belgium, originally from the UK. You can probably tell from the accent. So I mainly work on all things to do with massive stars, but particular focus on astroseismology, occasionally delving into things like magnetism, binarity, and spectroscopy and things like that. Very particularly interested in trying to calibrate 1D stellar evolution codes. So I think the discussion from this morning was a fantastic example, and that's made me very nervous about our session. So that's a tough act to follow. So thank you to those who are involved. I guess if the online people don't mind, then I'll give my thoughts on how we decided to sort of best handle this. So we had a couple of several questions actually from the conference organizers to make us do some work and think about things that are worth discussing. In no particular order, I suggest we kind of just go through them, and then each of us can sort of say our piece, but we really want to hear from everyone in the room. And if a topic is not interesting, then you should say that as a comment, and we move on to the next one, rather than us waiting around for things that are not particularly interesting to maybe this group of people. I think that sounds like a good plan. You see, look, feedback already. This is good. Thank you. Okay, I guess the first question that we were given, which we've put a bit of thought into, is so in this grand picture of observations. So that's you thought 1D modeling was a broad topic. Observations is quite broad. So I think what's nice about our panel is we each come from a different aspect potentially, and we're trying to combine those different things and give you a good overview. So the very big open question at the start of this discussion was, what are the major open questions still in the field? So the field being observations, let's say. Does someone want to get started on the online side?
I'm happy to say some things so it's just things that we're interested, right? Open questions.
Sure.
I'm coming to this from the perspective of thinking about open clusters, and in particular lower mass stars in those systems. So, you know, 3 solar masses or lower tend to be where I start to be interested. I'm interested in stellar rotation and stellar variability in cluster systems. And so some of the open questions, and maybe I'll just pause and if anyone wants to say anything as I'm going. Or just do one at a time and I guess switch off. But one of the things is that it's important to probe the occurrence rates of low mass stars in coeval systems and clusters and associations to adequately constrain the low mass end of the IMF. I'm very interested in lower mass stars and using infrared capabilities with things like Roman to try to measure with more precision the low mass end of the IMF. And I think Roman in particular has a lot of potential to help us there. In addition to looking for isolated planetary mass objects and brown dwarfs and with transits and things like that as well. But on the star side of things, I think that's particularly exciting.
Yeah, I think with stellar chemistry, there's way too much, way too many open questions that span a broad range of things. One of the things that we've been really interested in my group is, the chemical homogeneity of structures across the Milky Way. And in order to do that, really, you need to derive really detailed and precise chemical abundances. And so the question is, how do you do that? And what can those precise abundances tell you, not only about the galaxy, but also about the internal processes going on inside of stars? And so one of the things that I've been very interested in is especially looking at the chemical composition changes along the giant branch, which can constrain things like mixing. So how much mixing, how much extra mixing is going on at the ascent of the first ascent on the giant branch. What exactly happens at the helium flash, I think, would be something that I'm extremely excited about in terms of what we can learn from the stellar chemistry. But the challenge with stellar spectroscopy, I think, is really going to be interpreting the spectra. So there's data-driven approaches, there's traditional approaches for doing this, but regardless of which method you use, the reality is that our understanding of the atomic and molecular opacities and the line transition probabilities is still pretty poor. And so one of the big open questions outside of, I think, or inside of stellar spectroscopy, but a little bit outside and more in laboratory science, is really constraining the line list information that allows us to interpret the spectra that we're getting, both on the ground and in space. So that's something to consider.
Okay, and Trevor?
Yeah. So I guess my answer to this question is both very specific, but also very broad. I think a really interesting open question is, at least from the observation side, what are the final fates of stars, specifically between 15 and 30 solar masses? I think that's a really interesting regime in mass, because somewhere in there is a dividing line between stars that evolve to become red supergiants and explode as type 2p supernovae, and above that line, stars just do something else. And exactly where that line is and what that something else is, whether it's direct collapse into a black hole or mass loss, both through stellar winds and binary interactions to produce strict envelope stars like Yuval was talking about earlier in the session, that all of those questions center a lot on things like mixing and mass loss well after stars have left the main sequence, where we have some really poor observational constraints. And so I think there's a lot of really exciting work left to be done, specifically in this bin of initial mass space.
And for my part, my comments are really in line with what Trevor's just said. So I basically identified these three major themes as I see them. So the mixing inside stars is incredibly important in defining their evolutionary both end product, but also just their path through the HR diagram. So that's number one. And you can put under the umbrella of mixing various things. There's many parameters that you can choose to turn on or off in your favorite code. And if you turn them on, then you have to choose something for them potentially. And then we had the excellent review talk from Ilva. So I'm only going to repeat what she said here, that binarity is extremely important. And this is something that we really don't have very good benchmarks for. So something that I guess I could pick up from what Jen was saying in her review talk this morning of finding these benchmark stars. And I think Jamie also made a comment about wanting to do this for different masses. It's actually really hard to do this for massive stars, because the sun is something we know very well, and we can kind of scale to the sun. But what is that one O-type star? What is that one B star that we want to scale to? And I would say that the diversity is just so high in those sorts of massive star regime that it's difficult to actually choose the scaling. What is the Rosetta Stone? And if you end up with multiple Rosetta Stones, then you're kind of overusing that analogy a little bit. So yes, you've got the mixing within your models, you've got the binarity, and then what Yorick has already mentioned is the mass loss and the prescriptions that we have for how stars change their birth mass as a function of age. And so you can put the three things. I'm not going to touch magnetism because I don't know how to do that, but you can get some constraints from that. But that's a major theme that actually probably deserves a whole conference within itself. So we can only add it as a potential fourth theme here, but it's related to the previous ones that I've talked about. What did we miss?
I had a few more. So stellar rotation rates are lacking for low mass stars and extremely old clusters. And these clusters are extremely crowded, and prior space-based time series photometry has relied on instruments with fairly large pixel sizes. So I'm excited about the potential for something like Roman to do a long baseline investigation with the 0.1 arcsecond precision. And there's been a few different Roman RFI proposals that I've gone in looking at that in particular. I think that would be exciting. We haven't been able to achieve in the past the sensitivity to measure pulsations in brown dwarfs, and Roman could help either directly detect pulsations or reduce the current upper limit as it stands. And then lastly, on the side of binaries, I'm part of the WIN Open Cluster Survey here, and they've done a really great job of, in the last 20 years, looking for close binary companions. But there's not a lot that's been done in terms of more distant companions, so around 1,000 days or longer period orbits. And so I think we'll start to see the next phase of that. And I'm interested in how that will impact binary fractions and our understanding about stellar multiples. And that's everything.
Thanks.
I'm sure there's more, but that's everything I have.
So are there any major themes that coming from the observational perspective that you would wish to educate us observers on that we should go and search for?
Hi, Daniel Quine. This is, it's kind of related to something that Keith mentioned, and is also something that was mentioned this morning, this idea that in order to interpret various observations, we need to it sounds like a big problem is uncertainties about opacity, transition probabilities, things like that, things that maybe could be addressed with more lab data, or maybe better theoretical modeling on that type of physics. And I was just wondering if, to what extent is this like a major issue, and if there's anyone here who knows kind of where that's going, are we going to have better inputs for our models, good enough that for interpreting the observational data like over the next decade or however long?
Keith, do you have a comment on that? Yeah.
Yeah, so I think, one of the things that I often say about spectroscopy is that it's somewhat of a dark art. And so I like to say that I'm the professor of the dark arts. But at some level, the uncertainties in the line list, molecular opacities and atomic opacities really can affect the systematic uncertainties in terms of the derivation of the abundances, or the stellar parameters, that is the temperature, surface gravity, metallicity, microturbulence, B sin I, whatever. And so that can cause severe problems when you're wanting to make accurate comparisons between the chemical abundances of different structures in the Milky Way, or even if you're interested in looking at, even mixing processes and you want to understand how that affects the internal chemical composition of the star. And so there's been a lot of work done on the laboratory side to get accurate transition probabilities, particularly for atoms. It is very difficult work, and it's poorly supported. And this is the reason why most of the labs that support this kind of work are generally like well-established, labs that have been going for many years. And so there needs to be some incentive for people to go into this field. Molecular opacities is even harder to do, and but there's a lot of interest in it because of the M dwarf community and the low mass star community, because molecules just dominate the overall spectrum. And so I see that I would guess in the next 5 or 10 years, I mean, even the decadal survey, mentions this. And so I suspect in the next 5 or 10 years, we're going to see quite a lot of effort pushed towards trying to understand the opacities and the line transition probabilities. That said, there's a really wonderful survey that came out of Europe, the GAISO survey, where they fixed the line list, they fixed the model atmosphere inputs, they fixed all this stuff. And they had 8 separate at least I think 8 separate nodes, if I remember correctly, derive abundances for the same spectra coming out of ESO VLT, and they got very different results. So there's also a pipeline problem in terms of how we do the radiative transfer, how we synthesize spectrum, how we go from spectrum to abundances. And that's the other side of this problem. So in the meantime, one of the things that I think we can do to avoid a lot of this is make sure that we're doing differential analyses where we're focusing on getting the same spectrum and doing everything in the same way for the same type of stars, so that by doing it differentially, we can actually avoid a lot of the systematics. But that's what we have to do in the meantime. I think there's still a lot of work to do on the laboratory side. Better modeling, as far as I understand, better modeling of the atomic and molecular information is certainly a good way to go, but I don't know how much that's going to help relative to the laboratory, because you're still anchored to theoretical values. So there's a lot of work coming out of places that I know in Europe, as well as some places here in the States, on particularly doing modeling of NLTE corrections that are required for model atmospheres or for atmospheres. But I would say the laboratory side is probably where I think there's could be a lot of growth in the next 5 or 10 years.
Yeah, I completely agree with Keith. It is a tremendous amount of work to get this opacity data, and actually, I can't remember which MESA paper it was. Was it number 3? It was the 2015 one, where just from the perspective of thanks, Jared, for the massive star instability regions where we expect these pulsations to occur. It's a very different answer if you use OP versus OPAL as an example, and that's particularly to do with like ion abundances, because this is very important in the driving of oscillations, because they're excited at that kappa bump, the kappa mechanism in the opacity bump near the envelope. So there are a couple of ways I think you can go about this. You can do the experiments. You can tell the observers what the opacities are. But one of the things that's been happening in the last few years from the astroseismic perspective is you can actually predict what opacities you need based on the properties of the pulsations that you find. So in certain stars within the sort of 10 to 20-ish solar masses on the main sequence, as I said, those pulsations are driven by mainly ion opacity, and you have a distribution of frequencies in a star that are excited. And then you can just play around with the opacity tables to match what you see. And actually, a lot of the work that's been done in this is saying, well, we need ion to be about twice as abundant as in that particular region to actually explain the oscillations. So there's a nice complementarity between these two things. And if we tell people who do the experiments where to go and focus their energy, and then they tell us where we should focus our energy, I think that's a very good way forward.
Hi, I'm Joel Ong, Yale.
I can't see, sorry. Oh, there you are. Yeah.
So, hi. In addition to the well-established observational techniques that the panel are experts in, I was wondering if you would like to perhaps also discuss the development of new observational techniques, such as interferometric radii or disk imaging, and how that might help constrain the problems that we discussed today.
That's a good question. I don't want to dominate, so if people online should speak up if they want to.
I also don't want to dominate. So if anyone else has comments, please interject. But one of the things that we've been working on, and I got into this when I was at Cambridge, is the Gaia benchmark stars. And these are kind of ideal standards that each survey should observe in order to calibrate. And one of the things that are required essentially for these benchmark stars is that they have interferometric radii that we can then use the Stefan-Boltzmann law to derive, say, effective temperatures without having to go through things like spectrum. And this is especially important for the metal poor stars, where NLTE effects can be really significant and really screw up your analysis for the stellar parameters. And so I see these types of techniques becoming, well, at least interferometry becoming extremely important for benchmarking stars. But my understanding is that for interferometry, you need very bright stars. And so we're still quite limited by the technology in terms of what we can do with it. But I think there's a lot of work that's been done on interferometry with benchmark stars, and I think there's been some interesting work with Betelgeuse and interferometry as well. So I see these types of techniques as being extraordinarily valuable, but also very limiting, at least in the interferometry, very limiting by particularly the magnitude.
Yep, I agree.
Yeah. And I guess I can add a little bit on, especially with regards to like interferometry and Betelgeuse. I think there's been a lot of really exciting work being done to forward model things like interferometric data, or I know the Bright collaboration's been doing some really exciting stuff to try to back out the surface properties of some stars that have been observed by the Bright constellation. I know that there's been a little bit less work done exploring the reverse problem, trying to actually see which distribution of surface features and which parameters are actually consistent with the data, and also trying to understand where we actually can't make constraints. I know in a lot of these inversion problems, there's quite a large null space where you can't say whether you're seeing a large polar spot or a small equatorial spot, for example. And so I think kind of one interesting tangent that should be happening with all of this really exciting work is exploring that null space and trying to see whether or not we're actually sensitive to, you know, stranger or more exciting things than we get just from trying to match the observations with a forward model.
Yep, I agree. Something that I was thinking about this morning and over lunch as well. So Jen gave us the overview of like the best precision on certain observables that one might use to calibrate your evolution models, and then maybe a more average case on things like effective temperature and interferometric radii, for example, is something else you can use. And it occurred to me that, and I set this as a challenge actually, maybe we can have a small poll on this. Is there such a thing as a model independent observable? So a lot of these things that we use are actually in themselves, we call them observables, but effective temperature is a model dependent quantity. It depends on how well you understand the atmosphere of the star. Joel, please.
So I'm again, Joel here, I'm again qualifying that I'm by no means a solar person, but I'm given to understand that in helioseismology, the results from inversion, that is to say the sound speed profile and density profile, is supposed to be independent of the initial model you use as a starting guess for the solar structure.
I think that's probably true, but when people describe this, just like you and I have just mentioned this, supposed to be, and I would like to understand that personally about the dependence on that, because I know for other structure inversions that you are extremely dependent on the model parameter space. The sun is special for obvious reasons, so maybe that statement is true, but the only thing that I can, sorry, Rafa, please.
Yeah, just to say, in the inversions, the kernel are not, are dependent on the models. So although the inversion it's only observationally dependent, you have to go through the kernels and then you need a model. So that's a problem of the inversion. One of the problems of the inversion.
Yep. So the only one that I could think of is dynamical masses and radii in the case of eclipsing binaries. When you've got an SB2 system. That's probably the best case. That's one of the more well-known Keplerian problems to solve. But I see Yorick has got his hand up.
Well, it was more related to the earlier about new techniques, and interferometry is mentioned to measure geometry. But another way to measure geometry is with linear polarimetry. We have the sun, and we can see it from nearby. But what does a massive star look like, for instance, really? I mean, we think stars are spherical, and to some degree they are, but on small scale they're 3D, clumpy. And if we understand mass loss, we definitely need to look at the 3D structure. And also for binary interaction, for instance, we need more geometric information about what's happening.
Vicky.
Hi, Vicky Antochi here. I would like to come back to this calibration issue. I remember from all the conferences from the Kepler during the Kepler era, one of the main messages was actually that the sun is not a sun-like star. So I was wondering, what's your thoughts about that? Still using the sun for obvious reasons as the only calibrator at the moment.
That's a very good question. Maybe you could elaborate a little bit on I don't remember specifically why the sun was described as not a sun-like star.
So I'm not an expert on sun-like stars. I guess we have more here in the room, but as far as I remember, at least when it comes to activity, stellar activity, the sun is not as active as it should be, for example.
So Rafael Garcia again. Yeah, it's exactly that point. So the sun is a solar-like star, considering the same activity regime and oscillations. So if you go, then the question would be, is the activity of the sun the normal activity of a solar-like star with a one mass, etc., etc.? That's another different question. But if you consider the activity of the sun, and you put it in another and look for stars with the same activity level, then the sun is a perfectly normal star. This is what we think. And it seems to be that many of the stars are also oscillating, have the same kind of levels of activity than the sun, even in the Kepler field.
So this would be based on things like spot numbers and RHK and things like that?
Yeah.
Yeah, okay.
So, if you take the Kepler data, it's directly with the magnetic proxy from the light curves directly, because we don't have calcium HK for 20,000 solar-like kind of analogs. So if you take these, then under rotation periods, etc., it seems that the sun does not seem very different from the other stars in the Kepler set with the same vicinity of parameters.
Oh, yep. Sorry, Melinda. Yep.
Yeah, and I just also wanted to point out, in other stellar analog studies where you take stars that are similar in mass and similar in terms of their iron composition, and their surface gravity for their evolutionary state, there's some abundances that are quite different. Lithium being one that really sticks out, that the sun is quite lithium poor compared to solar analogs, and so that's interesting. Why that would be.
Anyone thought of any model-independent observables?
I can add something really quick, which is I don't think there are any from a very realistic standpoint of, the spectrum that you might publish that you've taken an observation of. That spectrum is itself a model of the 2D, unflat fielded, unwavelength corrected. There's so many systematics that just come from reducing data. And sometimes those can be very small, but sometimes, like in the case of measuring transit depths of planets, which should give us a model independent radius of the planet relative to the radius of the star, that transit depth depends on exactly how the pipeline that gave you your transit light curve produced that light curve. And so I think from a very practical sense, even these measurements that don't at least have a model associated with them are still kind of model dependent.
Yeah, absolutely. Yeah. So the point about differential studies, I think, is very, very important. There was a paper from either this year or last year from Pierre Maxted looking at an eclipsing binary system. So I think it was AI Phoenicius, where they did exactly that. They looked at the new test data of a very well-known eclipsing binary system, 2 low mass stars, and modeled it with various binary codes. And they were all fairly consistent, and their masses were all within 1 or 2 sigma of each other. And this is a mass precision of less than 1%. So those sorts of studies are, I think, are extremely valuable to try and benchmark different codes, to try and disentangle the observational, the instrumentation, and the model uncertainty. Jen. Yeah, I don't think it's on.
Sorry, there's a little bit of topic lag. I was just going to make a comment about the sun being a sun-like star. To add to Rafa's comment, that most of those things that people look at, activity, magnetism, rotation, all of those places where there's been claims the sun is not sun-like are pretty much on the hairy edge of detectability in many cases. It's real dicey if you were to have Kepler pointed at the sun and put the sun at a Kepler star distance, whether you would see pretty much any of the things we know are true about the sun from it. So I think that's part of the nebulous question of the sun being a sun-like star that's important here.
Will those sorts of things improve with Plato, for example, if we expect sensitivity to go as it should?
Okay, so Rafa Garcia again. From the activity point of view, the short answer will be probably no. But because these are bright stars, we'll have all the complementary measurements from Earth, so calcium HK, etc. So we will add a bunch of observations that we cannot do for many stars in Kepler. So for that point of view, yeah, definitely yes. And dropping also another idea that we always look for solar analogs for the point of view of the star, but the sun has a planetary system around, and this also should be taken into account at some point in the evolution of the system. So don't forget that there are planets around the sun. I mean, it's good for us.
Any other comments before I pick a random question? Yeah, please.
Daniel Lequene. So again, doing a bit of topic lag here. There was someone mentioned issues with data reduction. So as someone who just like runs simulations, I don't know anything about data. And I was just maybe everyone else knows this, but I thought, like for instance, in Rafa's talk, I thought it was very interesting to hear a bit more of the details of how they are doing the light curves and issues that come from that. If maybe someone could just say a minute or two about what are the types of issues that might come about due to data reduction that someone who's doing simulations maybe doesn't appreciate and would be good for us to keep in mind in interpreting observational papers.
Do you have a particular type of observation that you're talking about?
No.
Okay. Yeah, Keith, please go ahead.
I can quickly answer this on the spectroscopic side, and the answer is a lot. There's a paper from Charlie Oshry that we wrote where it was appropriately called "Opening Pandora's Box," because there are just so many things that could go wrong with reduction. So one of the things with reduction that can, some of the things that can go wrong is like if you're looking at spectra, things like, did you properly flat field the data? Did it, what does the scattered light look like? Is it very large? One of the biggest concerns with spectra reduction is where do you place the continuums? This is extremely important with a shell spectra where you have, all these orders, order by order by order. And in order to stitch the orders together, you have to continue normalize first and then stitch it, or that's what people normally do. And, where is the continuum? Especially when you start getting to the cool stars, there might not be any continuum left. So where you're placing the continuum can change the abundances by 0.05 dex, 0.1 dex, especially for very weak lines. And so this is particularly true if you're interested in like the heavy elements, the neutron capture elements and so forth, or things like that. And so these are some of the things that can go wrong when you're dealing with spectra. And this is part of the reason why different codes will give you completely different answers, because some codes use pseudo-continuums, some codes do a continuum on the whole spectrum, and so these are just some of the things, but there are so many things that can go wrong when you're doing data reduction. And that's part of the reason why I think of spectroscopy a little bit as a dark art.
Yeah, Trevor or Melinda, do you have anything you'd like to add?
Something that's just coming to mind right now, just thinking about, stellar activity and some of the difficulties in terms of getting better there, improving that with future surveys. One thing that is quite exciting is the ability to look at many of these stars in a panchromatic fashion. So, things like the Rubin Observatory from the ground, Roman from space, for instance. I'm sorry, I'm Team Roman right now. But what's exciting about that is, for example, young stars, brown dwarfs, IPMOs, these are objects that exhibit high levels of photometric variability. And it's difficult to distinguish that from transits in an achromatic light curve. But if you have color information, you can break some of those degeneracies. So I think that the panchromatic observations will have a lot to offer, breaking some of that degenerate information for stars and low mass objects.
One thing I wanted to quickly add is that, one of the best things to do is to get as close to the raw data as you can when you're trying to make inferences. It's very difficult to do that, but that's what you in principle want to do. And so I remember having a conversation back when I was at Flatiron Institute, years ago, about, is it possible? And this is something that I don't know if it's going to be possible to do this. But a pie in the sky idea is, instead of actually doing any kind of data reduction, let's take raw spectra from the telescope and go directly from raw spectra to the inferences on the stellar parameters, the temperature, surface gravity, metallicity, and the abundances. But the computation that's required to do that, and all the modeling that has to be done about the instrument specifics, is so challenging that I think that's why it hasn't been done. But that's something that maybe, X years in the future, that's something we might want to do, is actually just get back to just going from raw data to inference.
Yeah, and I guess I can add something as well, kind of in that vein, as well as kind of more on the like TESS Kepler data end of things. Like I mentioned earlier, that like your choice of pipeline can affect things like transit depths if you care about planets. So say, TESS's full frame images, which were observed at 30-minute cadence during its primary mission, and are now at 10-minute cadence during the extended mission. There's a lot of ways to go from those full frame images to a reduced light curve, and your choice of how you detrend those light curves. Do you try to get rid of as many of the things that aren't transits as possible? Because that makes a lot of assumptions about what is noise and what is astrophysically relevant, but still not a transit variability. If you're not interested in transits, how do you go about removing those kind of lower frequency systematics? There's things like co-trending basis vectors, where you pick kind of a few trends that best reproduce the light curves in a given region of the full frame image, and try to represent the light curve with those, and the residual is your light curve. But even then, if you're not simultaneously modeling that residual, then your fit to the raw light curve with those co-trending basis vectors might not be the best fit for the actual systematics. And so there's a lot of choices. And Keith, like you mentioned, this idea of doing it all from simultaneously modeling the instrument systematics and the astrophysical stuff, it just gets so complicated to do that all simultaneously. But really, those are all covariant with each other. Yeah.
Yeah, absolutely. I completely agree with Keith on the going back to the raw data as much as possible to try and understand your instrument. You need to understand what it's doing, and that sounds a bit trivial maybe if you're not an observer. But with a lot of these new large-scale surveys, it's the same instrumental settings usually for all stars. So you take things like TESS, there's a single exposure time. So some stars are saturated, some stars aren't. You've got maybe the calibration of things like color, position, time coordinate systems. All of these things are sometimes in pipelines and sometimes not. And sometimes when they're in the pipeline, there's uncertainties, and sometimes there's mistakes. So there was a notorious mistake in the Kepler pipeline, which forgot to take into account leap years. Who knew 2012 was a leap year, so they only found that afterwards. So really going back to the raw data rather than just looking at the pipeline output is very valuable, because that's the way you can trace these problems and improve those pipelines. I think Vicky, yeah.
So just so there is one thing which is also important, which is now we are moving to Bayesian world, and we need priors. So there are many things that we are doing in the data analysis that we also don't say usually in the conferences, etc., which is all the priors that we are putting, which is how well or bad we know actually what we are doing. And this is also something that we have to improve by a lot to get really good science from the data.
Mm-hmm.
Hi, Vicky here again. I would like to add one observable, and these are frequencies for this fancy astroseismology that we've heard a little bit about, and we'll hear about more tomorrow. It's actually not trivial to decide what are pulsation modes, because when you take a light curve from Kepler, TESS, or especially ground-based data, you will have a lot of peaks there that are not necessarily pulsation frequencies. You have amplitude variability, you have phase variability, and I'm talking now not about the stochastic oscillators, but more the intermediate to higher mass stars. We also have combination frequencies, which you still don't understand. So really deciding which ones are the proper modes. And sometimes it's easy to go lucky. They feed a model, but is this the right way to go? So there is a lot of decisions that we have to make in order to extract the perfect list. And also we have to keep in mind the moment we fit frequencies or we fit any signal to our data and extract it, we actually add potentially additional signals that we then interpret as astrophysical signals.
Yeah, absolutely. Yeah, there's a little bit of a running joke in seismology community that our errors are just too small. The data are so precise that the uncertainties on individual frequencies are in the 8th, 9th, 10th decimal place. It's incredibly, and you have to ask the question. You have to be honest with yourself and say, do you believe that? And if you do that forward problem from the raw data to the output of your frequency pipeline, yeah, it's not usually in the 8th decimal place. So you have to try and understand those things. Which is the largest term in your error budget, essentially. Sometimes we only pay a lot of attention to the last term, to the last step in the process, but there's a lot of steps before that which need attention. Oh, Melinda, please.
Oh, I just wanted to ask a clarifying question. I'm curious in the difficulty in determining the pulsational modes, how much of that is really limited by frequency resolution? If there were shorter integration times, are you able to work around that, or is this sort of a real physical limit that it's not instrument or observation dependent?
So perhaps I can comment on this a little bit. So one of the most bread and butter tools that we use is Fourier analysis to go from the time domain to the frequency domain. One of the powerful thing about that is that you get all the frequencies from that. But the interpretation usually ends, as Vicky says, you usually end up with a small fraction of the light curve being explained as pulsation modes. And one of the things that we have to make as an assumption is that these coherent oscillation modes are actually coherent. So the lifetime of a pulsation mode in a coherent oscillation is very, very long, infinitely longer than the data set. And so you'd expect a constant frequency, a constant amplitude, a constant phase. This is rarely observed, but in our analysis of time series, it's not so much limited by the resolution, it's limited by the coherency, I would say, in my opinion, of the oscillation. Because that uncertainty on the frequency is much larger than that 8th, 9th, 10th decimal place that you get when you assume a constant frequency with a data set such as Kepler. But just to say that is for the coherent oscillators, that's not an argument for stochastic oscillators.
Hi, Vicky again here. I would like to also add another comment to that. So I think it would help if we had shorter integration times, because it depends actually very much on what types of pulsations you're looking for. If you have short periods, then you want to integrate as short as possible, not only because you have to resolve them, but also because you may end up with amplitude attenuation. Mm-hmm. So if your signal is too close to the Nyquist, which is the highest frequency that you can detect, you will end up diluting your amplitudes, basically. So if you're after, if you don't do differential numbers, but rather you want absolute numbers, then you have to take this into account.
This is a very important point, actually, and a lot of the work from Kepler is very, very biased by this attenuation factor. So essentially, you're blind, completely blind at the sampling frequency of your instrument, because you're not going to see any variability if you're at the exact cadence of that intrinsic variability. Which means for a Kepler long cadence light curve, you're blind at something like 40-50 cycles per day. Sorry for the funny units. So if you're interested in stars that pulsate, and some of my pet favorite stars are Delta Scuti stars, they pulsate exactly in that range, which means that all of the results that we had from Kepler on those types of oscillations, we're only really looking at the sort of 10 to 20 cycles per day, because the amplitude attenuation drops off very sharply. And with TESS, there's been some nice work from Tim Bedding, for example, just saying that if you have a different sampling, you have a different telescope, different setup, not saying that one is better than the other, you can find these high frequency oscillations. It's just that Kepler was removing them because it's a sampling problem. So these sorts of things, we have to always, as observers, I think we have to be honest about the biases in those samples. The same is true for example, the red giants as well. If you've got pulsations that are very close to that Nyquist and that sampling frequency, you won't see the oscillations. So that introduces a bias in the sample statistics. Keith, you have your hand up, please go ahead.
I think that one of the important things, at least in the era we live, is it's so data rich that we shouldn't, at some level, right, you can predict where the frequency should be given what you can learn from the spectrum or vice versa. And so we should, in some sense, and this gets back to something that someone else said in the room, which is that we have prior information from all of these sources of data that we have available to us. Part of it is Kepler, part of it's spectroscopy, part of it's Gaia, parallaxes, and so forth. And it's part of the thing that I think we're going to want to do in the next 5 or so years is really begin to build models that account for the various types of information that we have. Because it used to be the case you'd only have a spectrum for a star, but you wouldn't have a parallax and you wouldn't have a photometric light curve. But now for many stars, we have all three of those things. And so I think it's time to start thinking about how we actually go about integrating all that information together to get out the inferences on the parameters that we're most interested in.
Absolutely.
Yeah, so Rafael Garcia again. So as it was said, there are two important things: the integration time and sampling rate. Sampling is the amplitude of the modes and the attenuation, but there is something else that we have not to forget, is that in the long cadence, many of the instrumental problems are removed on board, and the algorithms are not so powerful. And in fact, the long cadence data, it's much noisier than the short cadence data, because we do several of the removal on ground. So in fact, it's not only the amplitude attenuation, but in fact, we have much more noise, at least for the solar light pulsators. So we have an increase in the signal to noise ratio, which is much more important than simply the amplitude factor of the gain due to the sampling, because of this instrumental instrumental removal algorithm that are on board that should be simple, because we don't have the powerful on board to do all of these calculations that we can do on ground.
Yep, absolutely, yeah. So to bring it back to Daniel's question about what observations and observables can we trust, it's the same. The observers should do the exact same that modelers do, that simulators do. Is that essentially you need a resolution study, right? If you don't get the same answer from the long cadence Kepler data and the short cadence Kepler data, then you should take a step back and think about that, because that's probably the presentation of a bias in your star or your sample. So those sorts of factors are very important, and sometimes observers overlook them. Okay, one more, yep. Oh, sorry, Melinda, do you want to go ahead, and then Rafa?
Yeah, I just wanted to say, on a related note, we have to be very careful when even stitching different quarters or sectors together. So I know Ruth Angus has talked a lot about this with tests, that there are artifacts when you stitch sectors together, and so getting longer periods out of the test data, anything above 13.7 days, you should tread with caution. And also similarly, I'm seeing the same thing with Kepler when you're stitching together quarters. Those breaks in the rolls of each of those quarters introduce artifacts, and you're going to have them at those periods and the harmonics of those periods. And so just also being aware that there's limitations in even the same data sets in terms of what you can extract from it.
So yeah, Rafa again. So there is one thing that we haven't talked about, and it's extremely important, which is we have talked about the data, we have talked about the models, but then how we compare both. I give an example, the large spacing. We compute large spacing from a algorithm in the red giants, then we compare with the models. But depend on how the large spacing has been calculated in a global sense, in a local region around the NUMAX, etc. And then we compare with the models. And then how we compute this from the models. The physics is not the same. It's not that one is better than the other one. It's that the physics on each way of computing one quantity is different, and we have to be extremely cautious on how we do these things. And you have to talk together, modelers and observers, to just talk the same language and not just take the same letters explaining one variable with a physical meaning.
Yep. So that delta F is the frequency difference between consecutive radial order pressure modes in solar-like oscillators, and it's a function of radial order. So one might argue there is no such thing, because if something is not constant as a function of radial order, then the asymptotic definition may not be so good, but it's pretty good. But that is something that is calculated and observed to be offset from each other. All right, so one of the next questions that we discussed is what are the wish list items or surveys or data, maybe even tools to analyze the data that we're looking to produce in the next sort of 5 to 10 years or so. It can also be short term. Yeah, Vicky, please.
Hi, Vicky here again. Thanks for the question. I love this question because I have a lot of opinions about that. So I think what we are really missing are multicolor observations. I think Melinda already said it before. Mm-hmm. And for at least intermediate mass stars, and I'm pretty sure also for the more massive but also less massive, we really need to have simultaneous observations in multiple colors. We can only do more identification for a handful of stars without this multicolor photometry, but also in order to better understand what spots are, right? We need multicolor observations, and so on and so on. So if I could put my money on something, it would be multicolor photometry from space with the same quality of data as Kepler tests.
Ilva?
Okay, I'm not sure that I know enough. Oh, sorry, my name is Ilva. Just I. So I want to suggest spectropolarimeters for larger telescopes. When I was looking this up, it seems like spectropolarimeters are few and only exist for small-ish telescopes of 2 to 4 meters. So it would be great if we could do this for fainter stars and actually see magnetism on the surface. But it's just a wish list and something I'm really new in, so I don't know.
Yeah. No. There was a white paper on the archive. I think I've been up since 4 a.m. So I don't know if it was yesterday morning or this morning, but anyway, on UV polarimetry from space. I think Matt Schultz was the lead author on that white paper, with the various MIMES, Dynamics, and Bob usual suspects as well. So these are, I agree, things that are needed. Yeah.
Yeah, just for the wish list of Vicky, Plato is going to have 2 telescopes, one in red and one in blue. This is the fast cams with a 20-something second integration time. So there is not going to be a lot of stars, but you will have more than a few and much better than with Bright. So this is coming 2026. Well, at least you have 2, more than nothing.
Yeah, Trevor, please.
Yeah, so I guess this is a question. I really don't know as much about Plato as I should, but from what I have read, a lot of the focus of Plato is going to be on kind of lower mass stars, similar to the scope of the Kepler mission. Is Plato planning on observing more massive stars?
So the easy answer is yes, because the fields of Plato are going to be much larger than Kepler, and there's also going to be several fields. So there's going to be 2 long pointings and then a series of stop and stares, as they call them, similar to how Corot did this to look at different directions to try and probe different metallicity gradients within the galaxy, different types of stars. So yes, the core science of Plato is to find Eta Earth, to put it as such. But all of the extra physics that I think most people in this room are very interested in is under what we call the complementary science program. And the complementary science program, I think, corresponds to 8% of the targets, something like that, which is much larger than what Kepler had. I think Kepler, the seismic allocation for Kepler was 1%. And we're very proud that there are more seismology papers from Kepler than there were planet papers. So Plato is expected... Plato is expected to also deliver very good results for any sort of complementary science that is basically anything other than exoplanets in stellar astrophysics. Melinda, please.
I don't mean to change the topic, but on the wish list side of things, I would love to see a high resolution R of 100,000 or so space-based spectroscopy survey with a broad wavelength coverage to cover the infrared. There's a real dearth of M-dwarf abundance signatures, not only the number of elements, but the number of stars as well, so something like 200 last I checked. And unless you have a balloon experiment, you really do need to get pretty high above the atmosphere. So, that would be phenomenal. And I know getting mirrors into space is quite expensive, so probably not happening soon, but that would be my dream.
Yeah, Keith, you have your hand up as well.
Yeah, I think I want too many things, but the main thing that I think would be nice would be to have larger catalogs of ages for stars. Ages at the moment, I guess people are really interested in astroseismic ages or astroseismic masses. So large scale industrial scale astroseismic catalogs to compare with spectroscopy, I think would be super useful, not only for stars, understanding stellar evolution and the stars themselves, but also understanding the galaxy. We need ages in order to clock things like the Gaya-Salada sausage merger and other things. So I kind of have a foot in the world of stars, but also a foot in the world of the galaxy as a whole. And I think ages is one of the limiting factors at the moment.
Yeah. So under core science for Plato, there is the task, the ambitious task, to get astroseismic masses and radii to a few percent precision, and astroseismic ages to 10% precision. That is very, very good for FGK dwarfs. So that catalog will come because the field of view for Plato will be huge and include many of those stars. As I said, though, it's very ambitious, and hopefully we get pretty close to that. I see Falk. Do you have a hand? Yeah.
I have the microphone. Yes. So as someone who's doing simulations and theory, I'm a little bit lost with these expressions of importance and interest, because there must be some context that clearly I'm not fully aware of in terms of why do you want this? Why do you think this is really important? And that made me think that in general, as an observer or as a community, we can think of observations really I can come up with two categories into which I would put observations. You can design your observational program with the goal to discover something, discovery observations, and that's usually really cool. I mean, in the nuclear astrophysics community that I'd travel in a lot, people are trying to find the most metal poor stars, and so if you find one that is even more metal poor, then that's a Nature paper, and that might get you a job. So I understand the motivation to do discovery observations. At this meeting, we're trying to understand transport in stars, and what I want to suggest is that there is a different type of observation maybe that is needed to really nail transport in stars, and to sometimes, in order to have observational data sets that really allow us to distinguish between different physics processes that enhance our physics understanding, there's different types. I mean, you would design an observational study differently. You would maybe look at just a very few selected objects where you're really sure that, for example, this is a single star, it has 25 solar masses or 20 or whatever, it is there on the main sequence. This is how it looks like. This is not discovery observations, but this other type of observations, validation observations, are the ones that I think we really need, clean data sets that we really need to advance our and calibrate and validate our theories and simulations.
I completely agree. The difficulty is to find that calibrating star is quite a lot of work. So big surveys, for example. So that we saw the Hunter diagram earlier with the nitrogen as a function of V sin I. This was hundreds of hours of the largest telescopes in the world, sitting on very, very faint stars for a long, long time, just to get those single individual points. So I think the wish list for me is I think we do need these large-scale surveys. I agree with this sort of validation, and in the context of this workshop, I think the Hunter diagram is an excellent example of how we can understand transport from nitrogen, for example. So Ilva mentioned like the Ulysses and XShootU collaboration, which is going to look at a carefully selected sample of massive stars to study them and get as much as information as we can from those to repopulate that diagram and various other cases. And then there's other surveys, for example, like Foremost, very large-scale spectroscopic surveys that are also going to do those sorts of exercises. But it's very difficult for observers, I think, to say, here is the star to test all of your models against, because especially in the massive star community, I would not say that there's a prototypical example, that the diversity is very, very high. So I think we have to enter a regime of statistics and sample first to actually pick out which are the best stars, because they're all different and interesting for different reasons. And you said it yourself, we can be right for the wrong reasons without looking at the results in the wider context. Yeah, Trevor, please.
Yeah, just that I think this is a really interesting point that Falk you raised and Dominic you were just saying, and it's something that I think that exoplanet community is fantastic at. They have been, at least I've seen some really exciting papers saying, well, yes, if we have this space telescope with this resolution, with this blah 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 blah, you can find this. And I think that's something that that we as a stars community can really work on developing that, especially, Melinda, you mentioned a very high resolution space-based spectrograph. I think there's been a few mentions so far today of our capabilities in the ultraviolet. And the NASA Decadal just announced that there's going to be, hopefully, if pending budget stuff, there's going to be a 6+ meter space-based UV optical IR spectrograph. And while the instrumentation on that isn't decided yet, I think now is the time for us to say, well, look, if that telescope has a spectrograph with these capabilities, or if the coronagraph has such and such inner working angle, then we can really make that measurement. And that's both from making the case for these instruments, and also to help us make the cases decades down the line when we put in our proposals and we want the TAC to accept a STARS proposal over a planet's one. We need to start laying that groundwork now.
Mm-hmm. I think Vicky has the microphone.
Hi, Vicky here again. Another point in the wish list would be actually, now going back to already available data. So if you look at the Kepler input catalog, the test input catalog, and all these big surveys, they are mostly done to serve the low mass community because of exoplanets. So I would actually really wish to have catalogs that concentrate on the intermediate to higher mass stars, and I would love to hear if they exist, and I'm not aware of those. But I think it would be very important to actually have different to have those catalogs as well that concentrate on these parameters. And the other point, if I may add one wish list, is in terms of funding. Every time, so if you have a small telescope, it's relatively easy to get money to build a new spectrograph, for example. But getting money to maintain it over decades, that's almost impossible, because it's always about new, but maintaining already existing stuff is actually very complicated. Sorry to have changed the topic here.
Yeah, I agree. I want to come back to that point, but I want to also hear from Melinda and Keith. So Melinda, please, go ahead.
Just 2 points I wanted to touch on with a phase lag. One, you talked about for age diagnostics, astroseismology, really having a lot to offer. And I just want to be careful, depending on the mass range of interest, for lower mass objects, for things, 0.8 solar masses, 0.6 solar masses, you really are going to rely on mass period age relations to get precise ages. So it really depends on where you are in that parameter space. And then secondly, in talking about these upcoming missions, I really want to stress too that a few years out, when there are these calls, these community calls for white papers, you know, to get together and propose what you can do if you had maybe a slightly different filter, or, you know, just changing the parameters a little bit. There's sometimes flexibility to make changes and you know, for you to be able to discover and measure what you need. And so I think as a community, we need to really value white papers, and I think that we need to participate in that process so we can design the spacecrafts that we want to see, and that, you know, will benefit the community at large.
Absolutely. Keith, please.
Yeah, so I have a couple points. One is, which will jump around a little bit in topic. One of them is that, you know, on the conversation that was happening a little earlier on, you know, high quality information about a handful of stars to really constrain things like transport mechanisms inside of stars versus large scale surveys. I mean, the surveys, you know, have enabled us to not only find the one or two stars that we should be looking at, as was already mentioned, but in addition, these surveys are actually quite useful because there are population level things that are going on that could change transport mechanisms across, say, metallicity or across environment or other kinds of things that small sample with very high quality data is just not going to capture. And so the surveys offer an opportunity to see those population level effects. And that's I think one of the roles that the surveys will ultimately play in addition to. And then the second thing I just wanted to mention was that one of the challenges with the surveys is that they have largely focused on, you know, your typical lower mass FGK dwarfs or giants, but there are surveys out there that don't do that. So an example, kind of answering someone's question in the room, is there's the Lamos survey, which you know, while it does largely focus on FGK stars and it has an order 8 million low resolution RF2000 spectra, and there was a paper that came out recently where they've now actually gone in and looked at the chemical or the stellar properties of about 300,000 or 400,000 hot obese A stars. So there are surveys out there. One that I'm working with right now is HETDEX. It's a survey designed for, you know, dark energy. It has nothing to do with stars, but they have this is a massive multiplex low resolution survey. They can observe 34,000. They have 34,000 fibers on sky at any one time. They absolutely do not do any target selection. And so because of that, and whatever falls into the fiber, we have a spectrum of, and a lot of it is stars. And so we're working with that data set at the moment, just to see what we can get out of these low resolution spectra, because there is no target selection. So there's going to be surveys that are really focused on a particular regime, but there are other surveys like Lamos or like HETDEX, which really don't have target selections. And so doing these types of hot star catalogs or massive star catalogs is far more likely.
Absolutely, yeah. Does anyone have a hand up? I can't see everyone, but no.
Jamie here. So one thing I want to echo about Keith's large survey thing is the fact that a large survey, everything has been done the same way. Mm-hmm. So it's not always the right answer, but it's usually all wrong in the same way, which if you go back to the point about differential information, can actually be more useful than a single individual better point that is on a scale you don't know compared to a single individual better point that is on a scale you don't know. Mm-hmm. So. Yeah. You have to think really hard about what is actually the useful piece of information and where is your error coming from.
I think the example Jen gave in her talk this morning about those M dwarfs in a very, very thin, I think that I was amazed. I actually didn't know that. I thought that was fantastic. So Gaia did not care about that at all when it was designed, but there it was. I think that's fantastic that the models predicted that, and it was pretty close. But these surveys reveal the sort of diamonds in the rough, so to speak, when it comes to these predictions that the surveys call. You couldn't do that with any other mission other than Gaia, but Gaia didn't actually consider that. So yeah, the feedback that we give as a community to the design of these missions, if you have something like that in mind, I think is very important to pass that up the decision tree. Trevor?
Yeah, I just wanted to echo, that these ensemble measurements that we're getting from these large surveys are so incredibly exciting. I just agreed that Gaia plot from the talk earlier this morning was really cool. I think something that's going to be really exciting is that in the next couple of years, we're going to be starting to get data from the Rubin Observatory, and we're going to have an incredibly large ensemble of light curves with much worse cadence than something like TESS. But rather than, say, a couple hundred targets, like I might be able to get with TESS data, each of which has tens of thousands of observations, I'm going to be able to get as many stars as I could possibly grab with that data, with maybe hundreds of observations each, with multicolor observations as well. And so I think something that's really exciting going forward is kind of making these ensemble measurements where the high signal to noise measurements comes from your number of objects in your sample, not necessarily the qualities of the individual measurements themselves.
This is Daniel Lequene. I just wanted to reiterate something that Jamie mentioned this morning in the context of us discussing kind of what tools we would like in the future, that we are hoping that one of the outputs of this program and conference will be a white paper describing some of the things that we talked about and ideas for the future. So I hope that people who are interested will help contribute to that.
Absolutely, yeah. So the last question that we had on our list is completely open-ended, and it's something that Vicky mentioned about the funding of instruments, and so it's something that even I've noticed in my career, which is not that long, the change in the last 5-10 years or so of the attitude towards between designing and maintaining instruments. So if you're lucky enough to go to observatories on, like Lucia or Hawaii, for example, usually you see lots of empty telescope domes, and that's because what's inside is no longer supported financially, and that's usually person power, that's salaries, that's social security and things like that. The instrument is collecting dust, and it does not mean that the instrument is bad. They're usually very, very good. So the last question that we sort of discussed very briefly is, as a community, what can we do to try and support these, not only the instruments, but the people that are responsible for maintaining them, because it's harder and harder to actually get funding to support instrument scientists, for example, as much as it is to hire a postdoc to exploit the data. That's quite easy to do relatively, but to hire someone to build the instrument that's going to do all of these discoveries is relatively hard to do. So what can we do as a community to try and balance the scales a little bit in that regard? And I'm looking at people with tenured positions.
Jamie, I'll throw something out there. It would be great if there was a separate line and it wasn't competing, maintain one thing or build new thing, because build new thing always sounds more exciting, but maintaining things can also be valuable. It needs to be separated, I think.
Mm-hmm. I agree.
I'd just like to make, if I'm frank, I'd just like to make the comment that your comment about funding existing things also holds with software instruments as well as telescopes.
Yeah, absolutely. So I completely agree. The only reason I don't mention it is because this is the observation session, but I completely agree. Yeah. Oh yeah, sorry, Keith, please.
Should also count.
Sorry, Jamie?
Spectroscopic pipelines should also count.
Yeah, there's an inordinate number of spectrographs on the planet which do not have pipelines. It's remarkable. If you've never understood that, I don't know. I've never understood that. But you build the thing, and then no one actually designs a pipeline to extract the information. And then the telescope discontinues the instrument. So that's very, very, very interesting politically. But anyway, Keith, please go ahead.
Yeah, I think this problem is one that I've wrestled with now for a little while, because I had the fortune or non-fortune of serving on the decadal survey on the panel on enabling foundations, which exactly tried to answer this question. I, as a junior, I'm an assistant professor, so I'm a junior person in the field, or I still consider myself a junior person in the field. And it was horrifying. I was horrified to learn kind of the kind of out of balance portfolio that astronomy has. One of the things that I think is going to be hard to swallow, but our wish lists for our big telescopes needs to maybe consider the fact that people have to be supported. And so one of the things that astronomy often does is we build these massively large telescopes that cost enormous amounts of money, and then effectively don't support the cost of actually doing the science, because that comes from something like the NSF AST grants. And so, which acceptance rates are extremely low. And so one of the things that we need to think about when we're thinking about building telescopes, whether it's space-based or ground-based new telescopes, is every new telescope should come with a pot of money, a specific pot of money to support the science that's actually going to be done, which means that operations cost is going to go up, which means that you probably can't build your massively large telescope that you might want. And so, and that, in addition to that, we also have to think on the side of the legacy telescopes that already are in existence that are collecting dust as well. And so as a community, we need to think carefully about these particular things. The other thing I worry a little bit about in this regard is the telescopes are growing to be so large that only really qualified, trained folks are actually able to use those telescopes. And so what's happening is that there's a whole crop of young astronomers who've never gone to a telescope and have no idea what data reduction is like, who are observers who have no idea what data reduction is like because they've never had to do it. And so that's something that we need to think about it also as a community, is who are the people that are going to run these telescopes and how are they going to get trained if none of the legacy telescopes are in operation. So these are all things that we really need to consider as a field, but I think it really starts with making the really tough decisions sometimes not to build the really big telescopes in lieu of making sure that we have funds to support the people that are doing the science.
Yeah, very articulately put. Thank you, Keith.
Yeah, it's Daniel Lequene. Keith, I just want to ask a clarifying question so I understand what you mean. Are you saying that in the past, the way that people learned the real nitty-gritty dark arts of working with real data was by working on smaller projects, and now that we're shifting to almost all the support for larger projects, that doesn't exist, and because of that, people don't have that opportunity? Is that the issue?
Kind of. It's more of like the folks who are doing data reduction or analysis of spectra are usually, even if they're not going to the telescope, they're getting data from a Q-based telescope. But the reality is there's with these large surveys coming online and in many cases the really large telescopes, the ELTs that will come online in the 2020s, 2030s, there will be a very small group of people that will actually service those telescopes and actually run the data reduction and deal with the pipelines. And then everyone else will use the data. The problem with that is you're effectively getting tabular data. And I'm seeing this at least in many of the graduate students I talk to work with tabular data from these large surveys, but don't really have a clear sense of how the data is actually being produced, what the systematics are in the data, what the errors could be from data reduction, because they've never had to go through that process. So it's more than just that it's small or large scale, as opposed to like whether or not people are actively using the data. So a lot of the large scale surveys are producing and giving publicly their spectra. It's just a question of, do people actually use them or not? And I think that we need to ensure that our curriculums include how to actually do this type of data analysis and this data reduction and so forth, because otherwise it's going to get lost very quickly.
Mm-hmm. Thanks. I just want to quickly add that I feel like a lot of things that you're saying, I feel the same way about simulations as well, that there's lots of little details that can be missed if you don't start like from the ground up.
Just Vicky here. Just to comment on your question, I think I fully agree with what Keith said. I think that a lot of the recent observations were also triggered by the Kepler satellite that observed rather faint stars. And in order to actually really get the faint stars, or to get enough photons for the faint stars, you need to go to bigger telescopes. And I think now with TESS we have the option to actually realize that with 1 meter telescopes, we can actually already do very good observations of OBA, F, and other types of stars. This is something that Kepler did not allow us to do because the stars were too faint. And another comment in connection to that, concentrating on the bright stars. And I know that often the interesting ones are the faint ones, at least in my case. But it's worth thinking about going to space, not necessarily with missions like Kepler and TESS, but going into the nanosatellite business. Because there are actually several science cases that we can attack with small satellites, and nanosatellites have prices that even a university can afford. We're talking about $3-4 million for a mission that can last 2 to 3 years. So this is something that is affordable.
Absolutely. Trevor has his hand up.
I guess just to add one point on this, support for smaller telescopes, legacy instruments. I'm not 100% sure. I believe it is the Hectospec instrument, which is kind of similar to HET-DEX in that it has just I think 100 fibers on it that it can observe at once. And if you get data with Hectospec, there is one person who has the software on her computer. I'm pretty sure she's retired at this point. And so on her own time, she's not paid for this, she reduces Hectospec data and will send it to you. And that's it. If this person decides that she doesn't want to reduce these data anymore, again, totally out of the goodness of her heart, there goes that entire instrument. And so the fact that that is just a skill set that we no longer have, and yet we're still trying to build instruments that we want to support for a long time, something just doesn't quite add up there.
Oh, one could release the code publicly with full documentation, I guess, to fix that problem.
Absolutely. But in so many cases, these pipelines are built on this version of IRAF that worked on, and I'm pretty sure this is actually a part of the story, that this is one particular version of IRAF, and whether or not we want to continue being reliant on IRAF is also, I guess, another question. My answer is probably no. Yeah.
Keith?
I want to quickly add to that, which is that I think it's an absolutely good idea to release the code publicly and to have the community service it. The problem is incentive. And I'm sure that there are many people in the room that feel like that know this from firsthand, is that they're really, from a jobs perspective, there's no incentive to publicly maintain code. There's just no reason to do it, because you're not going to get your faculty job, you're not going to get tenure promotion from it. So unless you can make a very specific case. And so we need to, at some point, rethink a little bit the way that we structure our incentives in our jobs, I think, to incentivize that kind of attitude. And I think this is also true with data as well, although this is a much hairier subject. In the United States, many of the telescopes are private data, and so in many cases, there's no need to reduce or to release your data publicly. But in large swaths of Europe, because of the transnational nature of the VLT and other facilities like Gaia, the data is publicly released. And so the way that we do open science and the incentives for open science really need to be there, I think, in our jobs.
Yep.
Well, Keith just said everything I was going to say, but Meredith Joyce. But also, even posting everything open source publicly, that's not even enough. There still needs to be some kind of incentive to document that, update it, pay people to do that. And I feel like the software maintenance is an aspect of one of these reasons these observational pipelines fail as well, right? So there's the upkeep of the instrument, the upkeep of the knowledge, and then of course the upkeep of any code that accompanies that.
Yeah, the deprecation of IRAF is a fickle thing. And I promised myself at the end of my bachelor's I would never run it again, and I've kept my promise. But one has to keep on top of these things throughout the project. To release it at a late stage where it's so specific to a version on Windows 95 or whatever, it's difficult to do that at that final step. Yeah. I'm conscious of the time, so I guess we need to wrap up soon. Melinda, do you have something to add?
Yeah, I mean, this is a much broader topic, but I think it has to be mentioned. Part of the issue here is this frantic pace to put out results, to get the papers out. We have 1,500 papers a month. There's only so many seats. we're seeing higher education being increasingly turned into a corporation to make a profit, more adjunct faculty. I mean, I think we seriously have to, as a community at some point, have to really talk about the quality of work and the pace at which we must move if we really want to maintain databases, maintain instruments, write high quality papers. And I don't know how that happens, but I just feel like it has to be mentioned. And I hope it's something that we can continue to think about, because I worry that the quality of science in general is just being, it's being impacted by this sort of frenetic desire to get on this 10-year summit and this blood sport that astronomy sometimes feels like.
Yeah, Keith?
I completely agree with Melinda on that. I just wanted to say one last thing, which was that, one of the things is that the decadal survey does cover a lot of these topics in the state of the profession and the enabling foundations panels. But I would encourage you to actually read the appendices, which is actually the panel summary. It's a little different than the recommendations that came out from the main decadal steering panel, but they go in there. These appendices go into a lot more detail about some of these issues, including one of the recommendations, or one of the things that I think our panel came out with was like the idea that we would like to have like a centralized, national archiving center for astronomy that would actually have some of the that would actually work to maintain some of the codes and data across surveys and so forth. So a lot of the details that didn't necessarily make it all the way up to the steering panel can be found in the appendices.
Falk?
I'm feeling really old at this moment because I feel that, Falk Herwig, because realizing and stating that we're basically doing everything on a shoestring, and that is sort of really tiring and bad. This is something that is not new, I think, and so. And because it is not new, maybe my hope in the fact that we're stating it again and then it changes is relatively small. And I think, in a sense, if one can frame a weakness or a problem as an asset or something positive, that's maybe a way how to get out of it. And I think the fact is that in astronomy, we have a certain, like in the world, in each country it's a little bit different, but by and large, we have a certain fraction of the pie that we can use to do astronomy science, and that fraction will not dramatically change. If you want to do stuff in this fashion where you really know that certifiably you get the right answer, I mean, we have people here like Philip is at LANL and others have been working with the national labs where this equation of how do things to be resourced to really do them properly is different, and you get different outputs, but you also get a different price tag for that. And so what I'm thinking, what we should think about is I don't think that we have, just as a community, whether it's in observations or in codes, we have a tendency to just try the most crazy and push the envelope the most that we can with the available budget, and that is sometimes a very dirty business. But I think that it is an opportunity maybe also to think about how we can structure our collaborations, how we can structure reproducibility of science, take advantage of new technologies such as virtual research environments, and Dockerized environments, and so on and so forth, sharing processes. MESA, for example, is of course a big thing. These are all ways in which we can make our work more impactful and address these things. But I think that this sort of somewhat messy business, that's not really going to go away. It's just, I think, maybe part of how we do it, because we always want to push so hard to the next thing.
Perhaps one last thing, just to end on a positive note. I think it's a nice thing, and this obviously is a credit to the conference organizers and the program organizers in general, that there's so many junior people at this meeting. I think that shows a good sign of healthy influx of interest and people into the field of stellar astrophysics. So I think there are a lot of positives to that as well. Who are they?
But we should probably thank our panelists. We appreciate you so much for being here.